Today we are going to learn about mastering NumPy's linear algebra functions. You will acquire skills to perform matrix operations, solve linear equations, and understand key concepts such as eigenvalues and SVD using NumPy.
Welcome to our comprehensive guide on mastering NumPy's linear algebra functions. In this video, we'll explore how NumPy, a fundamental library in Python, provides powerful tools for performing linear algebraic operations. Whether you're a data scientist or an engineer, understanding these functions is essential for handling complex datasets and mathematical models. NumPy's linear algebra module offers a wide range of functions that streamline matrix operations, making problem solving more efficient. By the end of this session, you'll be equipped with the skills to perform matrix multiplications, calculate determinants, find eigenvalues and eigenvectors, and much more. Matrix multiplication is a fundamental operation in linear algebra, crucial for various applications in machine learning and data analysis. The numpy.dot function in NumPy allows you to perform dot products, also known as matrix multiplications, efficiently. This function takes two arrays as inputs and returns the dot product. For example, if you have two matrices, A and B, numpy.dot B will return the product of these matrices. Understanding how to compute matrix multiplications with numpy.dot is vital, as it is widely used in neural networks, computer graphics, and other fields that rely on large-scale computations. In practice, matrix multiplication is used to transform data, calculate distances, and perform other critical operations in data science tasks. Let's go through some practical examples to see how numpy.dot can be applied in real-world scenarios. The determinant of a matrix is a special number that can be calculated from its elements. It is a scalar value that provides important properties of the matrix, such as invertibility. In NumPy, the numpy.linalg.det function allows you to compute the determinant of a given square matrix. To use this function, you simply pass your matrix as an argument, like so. numpy.linalg.det matrix.determinants are essential in solving systems of linear equations, understanding linear transformations, and in various applications such as calculating the area or volume of geometrical shapes. By gaining proficiency in calculating determinants with NumPy, you enhance your ability to analyze and solve complex mathematical problems efficiently. Let's delve into an example to demonstrate how numpy.linalg.det works in practice. Eigenvalues and eigenvectors are critical concepts in linear algebra, used extensively in fields like data science, physics, and engineering. Eigenvalues are scalars, and eigenvectors are vectors associated with a square matrix. They are used to understand the properties of the matrix, such as its behavior under transformation. NumPy provides the numpy.linalg.ig function to compute the eigenvalues and eigenvectors of a matrix. This function returns a tuple with the first element being an array of eigenvalues and the second element being an array of the corresponding eigenvectors. Understanding how to compute and interpret these values is crucial for tasks like principal component analysis, PCA, which is widely used for dimensionality reduction in machine learning. We'll walk through an example to see how numpy.linalg.ig can be applied in real-world data analysis tasks. Solving systems of linear equations is a common challenge in data science and engineering. NumPy's numpy.linalg.solve function offers an efficient way to find solutions to these systems. When you have a system of equations represented in matrix form, x equals b, where a is the coefficient matrix, x is the variable vector, and b is the constant vector, you can use numpy.linalg.solve a, b, to find the vector x. This function is designed to handle large datasets, ensuring both efficiency and accuracy. Solving linear equations is vital for modeling and simulation tasks, such as circuit analysis, optimization problems, and predictive modeling. Let's explore a practical example to see how numpy.linalg.solve can be effectively utilized in solving real-world problems.
Singular value decomposition, SVD, is a powerful technique in linear algebra, used to decompose a matrix into three other matrices. It has numerous applications, particularly in data science, such as dimensionality reduction, noise reduction, and data compression. In NumPy, SVD can be performed using the numpy.linalg.svd function. This function returns three matrices, U, sigma, and V, which represent the decomposition of the original matrix. Understanding SVD is crucial for tasks like image processing, where it helps in compressing images without significant loss of quality. By mastering SVD with NumPy, you can tackle complex data analysis challenges more effectively. We'll look at an example to understand how SVD is implemented and interpreted using NumPy.
Matrix inversion is an essential operation in linear algebra, used to solve equations, calculate projections, and perform transformations. In NumPy, the numpy.linalg.inv function allows you to compute the inverse of a given square matrix. The inverse of a matrix A is another matrix, denoted as a to the power of -1, such that when it is multiplied by A, it results in the identity matrix. To use this function, simply pass your matrix as an argument. numpy.linalg.det matrix inversion is particularly important in data analysis for tasks like regression analysis and optimization. Understanding how to compute matrix inverses with NumPy enhances your ability to perform complex calculations and solve mathematical problems efficiently. Let's go through an example to illustrate how numpy.linalg.det is used in practice.
Linear algebra functions in NumPy have extensive practical applications in both data science and engineering. In data science, these functions are used to develop machine learning models, perform data transformations, and optimize algorithms. For example, matrix multiplications are crucial for neural networks, while SVD is used in recommendation systems and image compression. In engineering, linear algebra functions help in simulations, such as structural analysis and control systems. By mastering these functions, you can enhance the efficiency and accuracy of your computations, leading to better performance and outcomes in your projects. Understanding the real-world applications of these linear algebra functions is essential for leveraging their full potential in solving complex problems.
In conclusion, mastering NumPy's linear algebra functions equips you with the necessary skills to tackle complex mathematical and data analysis problems. We've covered essential functions like matrix multiplication, determinant calculation, eigenvalues and eigenvectors, solving linear equations, SVD, and matrix inversion. These functions are not only foundational for academic purposes but also have significant practical applications in data science and engineering. I encourage you to practice these functions and explore further resources to deepen your understanding. Thank you for joining us on this learning journey, and I hope you feel more confident in using NumPy for linear algebra tasks.